Hey, this is video 25.3. We're looking at more about electric potential, and in this case, we're going to be looking at the electric potential due to a point charge. Now remember, the definition of electric potential was V equals negative integral of E dot dx, where E is the electric field and dx is a short distance. And we're also going to say at infinity, the electric potential equals 0. So that's where we're going to start. If we've got a point charge here, so I'd call that plus Q, assume that it's positive for now, it produces electric field that point away from it. What we're going to do is we're going to bring a small test charge, Q naught, also positive, in from infinity. So it's going to start at infinity, and we're going to move it until it is a distance r away from this charge plus Q. Now at any given point along this line, the electric field points opposite dx. And that means that E dot dx is negative, and V equals negative E dx, and those negative signs cancel out. We also know that the electric field is equal to kq over r squared. The other interesting thing we can say is that dx, because we're pointing inward, dx is equal to negative dr, because if r is increasing, we're moving away from the point charge, but r is decreasing, and so our dx is negative dr. And what this works out to be is that the delta V equals the integral of kq over r squared times negative dr integrated from infinity to r, because we started at infinity, we ended a distance r away. So k and q are constants, so we get negative kq outside the front of the integral, and then dr over r squared. Now the integral of 1 over r squared is just negative 1 over r, so kq negative kq times negative 1 over r evaluated at r to infinity. The negative signs once again go away. This particular derivation, there's tons and tons of opportunities for sign errors. And so this ends up with kq over r is the electric potential. Because 1 over infinity is 0. That is an equation you should memorize. This particular derivation is not going to be on the AP exam, but you should know it because similar problems where you have to integrate the electric field to get V will be on the exam. You should memorize this expression for the potential due to a point charge. In this case, Q is the charge that is creating the potential around it, just like it is with the field. Q naught, notice, our test charge, doesn't show up at all in the equation. Now let's say we've got several point charges. Well, what we do is we find the potential for each of them and add the potentials up. What the equation sheet said is that the potential equals the sum over I of K times Qi over Ri, where Qi is the ith charge and Ri is the distance from our point to that charge. So this would be KQ1 over R1 plus KQ2 over R2 plus and so on. The idea is that you've got all these charges, Q1, Q2, Q3, dot, 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 and you've got your point where you're finding the potential, call that point P, and the distance between there and Q1 is R1, distance between there and Q2 is R2, distance between there and Q3 is R3, and so on. Now notice that because potential is a scalar, adding them up is very easy. We don't have to worry about components, we don't have to worry about directions, we just have numbers and we add those numbers up. And that means that finding the potential due to a collection of point charges is usually easier than finding the electric field due to point charges. And we'll actually find, well, at least you will when you get to upper level undergraduate physics, if you take that when we're actually calculating electric fields, usually what you do is you calculate the potential first, and then you take the derivative of that to get the electric field, because that's almost always easier than just calculating the electric field. Now we've got an example of how you do this. We've seen this particular arrangement of charges before. We calculated the electric field at point P, and I believe we found that the electric field at P was 0. Question is, does that mean the electric field, or the voltage at P, is 0? What the hell? I'm going to learn how to spell one of these days. So will potential be 0 there as well? Now, the first thing we have to do is find the potential due to the first charge up here, which, because it is the same charge and the same distance from point P as charge 1, produces the same voltage. And so that's K times the charge, which is 5Q, over the distance, which is D. The potential due to the third charge is K times its charge, 3Q, over its distance, which is also D. And the potential due to charge 4 is K times its charge, which is negative 12Q, divided by its distance, which is 2D. And that works out to negative 6KQ over D. Notice that a negative charge produces a negative potential. There's no directions, there's no vectors. It's just either a positive number or a negative number. Positive charges make positive potentials, negative charges make negative potentials. And then we add all of them up. So V1 plus V2 plus V3 plus V4. And that works out to be, let's see, we've got 10, 13 minus 6 is 7. 7KQ over D. It's a positive number, there's no direction. That tells us that while the electric field is 0, the potential is not. And that is generally the case, that the electric field being 0 does not mean the potential is 0, nor does 0 potential mean 0 electric field. And we'll get another illustration of that. Let's say we've got 4 charges in a square. If all 4 of them are positive, let's look at the potential, the electric field, and the electric potential at the center. So at the center there, because of symmetry, E is equal to 0. V will be positive. In fact, V will be very positive because it's close to 4 positive point charges. In another arrangement, we can make 0 potential, but not 0 field. fact, the field is going to point to the left, and the potential will be 0 because it is equidistant from the same number of positive and negative charges. What you should do, try to figure out a way to arrange these 4 charges, positive or negative, so that both electric field and potential are 0. And there's actually 6 different unique arrangements of charges for this, but I'll let you figure that out. I think there's one of your problems is something like this. What I'm going to check tomorrow are questions 2 through 4, which deal with calculations of potential due to point charges.